libraries even, which is because the Java class file format is pretty complex, and as you might expect, I cannot go into the depth of everything here today. But we will scratch so much of the surface that you will be able to read up everything you're interested in yourself by your own. And anyways, like with all coding, you have to try it out yourself anyways if you really want to understand it. And then summarizing, I want to show you the wider impact, why this will affect the way you can use Java in the future, because once you made the jump to Java 25, you will probably be able to update your JDKs regularly without updating your libraries. You will still have to do it sometimes, but all in all, I'm expecting that the pressure to update will disappear, which doesn't mean that you shouldn't update your libraries. Of course, you should do that, but if you worked for enterprise customers like I tend to do, besides doing a lot of open source, you know also what pain this causes. So it will make the Java ecosystem more robust, and yeah, that's been an ongoing effort. So to start out with something tangible, what is a Java class file? Sorry? Oh, you don't see my slides. Wait, then I have to probably move this here, and then press here, and hopefully you see my slides then. Great, and I see my slides here down. Nice. Okay, so what's a Java class file? The JVM, very fortunate for us, is a very well-defined language. If you've worked with PHP or other languages, those languages basically happen accidental. So someone implements PHP and then says, like, this is how it works, and you can observe how it works, and you can, of course, do this with the JVM. You can run a Java program, and you can observe the output, and then you can guess what a Java program is supposed to be and how it will work. The Java virtual machine, however, is very well specified. This means there's 2 documents on Oracle's web pages, which for every Java release define on many pages what everything is, how the language works, how the grammar is defined. And it does so for the Java language, but it also does so for the Java virtual machine. So if you want to implement your own JVM, and that's not only Oracle that does that in OpenJDK, there's other people who do it, obviously, you can look into the specification and find out what an expected behavior is. And in the Java virtual machine specification, there's a whole chapter, chapter 4, that defines the class file format. And if you compile a Java program, right, you have your Java code and you run the Java C tool, it will output a class file. And not only Java outputs a class file like that, also Kotlin will do that, and Scala will do that, and all the other languages that run on the JVM. And the class file is basically the common denominator, which makes them interact, right? Without a specification like this, if the JVM would execute Java code as source, you would have to transpile. You would have to translate Kotlin to Java, which is very hard. But instead, Kotlin compiler can look into the specification, look into how class files are supposed to look like, and compile their code to the same format such that the JVM can execute it. And if you read this chapter describes the class file format, such and such, and each class file contains a single class, interface, or module, and you can already say here, wait a minute, what about records, what about annotation types? Those don't exist on a class file level. Records are just classes, and annotations such as interfaces on the class file format. So the Java virtual machine is basically a reduction of Java's complexity to the basic concepts of it, and it then tells you how to read a class file. Because if we, and to have that noted, I'm talking here today, especially if you watch on video, the Java version 24. Every subsequent specification of the JVM might, of course, change a lot, and that happened in the past, right? Java 7 was very differently specified than Java 8 in terms of invoke dynamic and lambdas and so forth. So this is something that will be released formally, and then every user can basically look at the difference of the specifications and update their interpreters and JVMs. Right, so what is a class file? Very basically summarized, it's a sequence of bytes, and a byte array is, of course, it's a binary format, right? It's not text. It basically says, if you encounter this sequence of bytes, it will be a class file. And the most trivial class file we can encounter is a class foo that extends bar, and you can basically open a hex editor and create this class file yourself. Every Java class file starts with a magic number, which is Java trivia. I think a lot of people know that every class file starts with the hex representation of Cafe Babe. You can tell that Java was invented 30 years ago when you would still make a reference like that. And now it's engraved in the class file format forever. Because if those numbers are missing, the Java virtual machine will not even consider the file you're presenting to it as a class file as a Java class. After that, there's different things. There's the Cafe Babe, the minor major version. 44 is the hex representation for Java 24, for example. Then we have those, right? And we have a constant pool, also something you will encounter if you work with class files. Basically, every Java class file lists all strings and numbers and references in a list in the beginning of a class file. And this comes from the times when applets were a big thing, because you try to compress, right? Normally, a class file is not shipped as a class file. It's shipped in a jar file. A jar file is nothing more than a zip file where you would have deduplication to some degree. But in the old days, when you would stream Java classes through the browser as applets, it was important that you already did some deduplication, and all this legacy in the class file format is still around. Right? So foo extends bar, we will need 2 strings. We will need foo and bar and nothing else, because there's nothing else referenced. So we will have a constant pool count, which is ironically also one more than the count, which references that, and then we will have some bytes that state it's public. We will have some bytes that just point to the constant pool index of foo, which is the second entry, the class of foo. Then we have the super class, which is the class of bar. Then we have no interfaces, we have no fields, and we have no methods, and we have no attributes. Attributes, most famously, are annotations. So if you opened a hex editor on your computer and you would punch all these bytes in there and you would save it as a file, you would have generated a valid class file, which you can validate with this specification, right? So, what is the class file API? You can guess that nobody wants to open up a hex editor. So, since Java 24, there were of course libraries for that before, but since Java 24, OpenJDK has an API for that to create this byte sequence that is, according to the specification, a valid class file. And it will expose it to everybody through the Java base module. So any trivial Java program from now on will have access to this class file API. And you can already guess, I mean, Android, for example, doesn't use the Java class file format. This is parts of the big dispute that was between Oracle and Google around this. We will have to see if Android ever updates the Java 24 specification, how they're going to handle it, because it's very different. However, official Java, standard Java, which is all Java but Android more or less, will at least be able to do this. And you will be able to define class files the same way as we just did manually, but with a more readable API. So now we want to create this class, foo extends bar, right? How are we doing this? We will say class file of, creates an empty class file. Now we will say build. And now we will support a class description, which is foo. And then we will be passing a builder where we can say, okay, this class, we want public flags. We want to have the class public, because by default, everything is set to the default. The default visibility in Java is package private. Same goes for the class file API. And then we specify a superclass of type bar. If we don't specify one, implicitly, of course, object will be the supertype. And those implicit things, such as the Java compiler normally takes care for us, are added also by the class file API, so there's some convenience to it, but we will be operating on the class file format. So if we write this byte array to a file, foo.class, we will be able to look into the hex representation. Now, I won't go byte by byte, but if we compare this previous slide with the bytes that I spelled out here manually, with what we have created with the class file API, they will of course be exactly identical, right? And that's kind of the convenience. And this, in a nutshell, is what I'm here to present. So if you understood what I was talking about, so far, this is basically what the class file API is. And you can think of use. Who uses class file API? Mockito. which I'm working with, right? How do we use class file APIs? A mock is nothing more than the class that you have written, that you have compiled, and then we will take this class, we will use a so-called Java agent to modify it, so that if you mark an instance of a class as a mock, we basically manipulate the method where we, in the beginning of every method, check, is this instance a mock? If so, do Mockito stuff. If not, do the regular stuff. And that's what we need to do, right? We have to go into the class file, have to parse out what it is, what every byte means, and then we have to change the byte so that the class now represents what we want it to represent. Same goes for Hibernate. Uses your bean, and whenever you set a setter, you also change the flag of the dirty field to true, and then when you pass it to Hibernate, Hibernate will check if the flag is set to dirty, and if so, it will persist it down to the database and so forth. The same goes with Spring. How does Spring transactional work? It again checks there's an annotation present. If so, we add some code to the beginning of the method and open transaction and close it in the end. That's why Java libraries need class files. And if you're interested in the use of class files and so forth in class file manipulation, as I mentioned at the beginning, go to YouTube, punch my name, choose one of the 50 videos I've done on this, and you will be able to learn on that as well. But I'm not focusing on that today. Since this is the first time I'm talking about the class file API, I want to rather focus on this. Since it's a large topic. All right. However, now we created a boring class. So just to walk through quickly, to define a field, we will also have access flag. A public field will have the access flag 1, as the specification says. It will have a name, f. It will have a descriptor, mentioning the type here, which is a string. And it might have attributes. If it is annotated, it will be attributed. There will be the information about the annotation in there. And again, you have a potential use case. What does an annotation processor do? It won't load the classes and execute code. It will just go through the class file. It will find the attribute for annotations, and it will notify the API that something like this was found without even executing anything, right? Same goes for methods. Methods will have an access flag, methods will have a name, and they will have a descriptor. Descriptor is basically a concatenation of the parameter types and the return type, and those you might even have encountered in your career. Right? If you find a no such method error, those will leak the class file internals. They won't mention the Java names and Java type descriptions. As you see here, this is a so-called descriptor, the Spring Web Application context with the braces in front, which means no arguments, and the L in front of the type, meaning this is a class type, an object type, and not a primitive type, where, for example, integer would be I, and not int. So this is just also interesting to know for that reason, because you might have to debug these things at some point, and then you know how to read this and why it looks like that, right? Right? And these attributes, of course, you can also, and attributes. These attributes, you can also define custom. That is a nice property of the class file format. There's no limit to it. What you can add. You can have a custom compiler that adds custom information to class files that only your compiler is aware of. Again, this is very important to languages like Scala, like Kotlin, where you might want to embed information about a class file that isn't relevant to the JVM, that isn't relevant to the Java language, but that might be relevant to Kotlin again, right? You have a Kotlin compiled library, and your Kotlin classes might contain information that is only relevant to Kotlin. So you can embed this as a custom annotation, and your Kotlin compiler might then read this information and make use of it in a way that the JVM doesn't know about, right? So you can add whatever you want. Of course, you might wonder, where does code go? Where does things like sealed interfaces go? And all these things also are attributes. So every time the JVM introduces something new, and might it be as trivial as code to execute, it adds a new attribute. And those you can also find in the class file. You have constant values, which is the constant value of a field. You have the code, as I mentioned, like the method implementation. And you have nest host, nest members. You have many, many more that are all described in the Java specification. I won't go through them in detail. They have different relevancy. For example, these you might well know, annotations. the irony of annotations is that the JVM itself doesn't care about annotations. The JVM will never process annotations. It will never do logic based on annotations. It's just metadata. So for the JVM itself, you could just remove the annotation feature and it wouldn't have a consequence, right? Even modules are just considered by class loaders, not by the JVM itself. Okay, so let's rather look at a real class file. You've seen the trivial one I've shown you before. Do you think it's going to be as small as the class file we've seen before? Well, of course not, because Java-C adds a lot of stuff. It will add a default constructor, for example. It will add attributes like the code attribute, because a default constructor isn't empty. It will add a line number table so that you can debug your Java application, and it will also reference the source file to allow debugging and so forth. So in reality, class files are big, and of course for that reason also it's fully unrealistic that you walk through a class file manually with a hex editor like I show you now. And even though I've been working with class file manipulation my entire career, I've done it maybe once or twice in very rare scenarios. In reality, I will of course use tooling. So let's expand a bit on how this new class file API is working, right? So we already added foo and we made it subclass bar. How do I add a field? And of course, you can expand this concept, class builder with field. And now you can supply a method, a field type, a string, right? It's the constable. And that is also introduced to prepare this API. A constable is basically just this class desk that we shown before, and every loaded class can be transferred to one. It's a bit annoying. You have to still return optional because there's a concept of hidden classes, which is used in combination with lambda expressions and so forth, which I won't go into either. So in theory, not every class has a constable description that you can reference, a name. So there's a lot of or else throw in this code. But then we say, all right, we define a field f, and then we'll make it public. Now you already have created a class file, foo extends bar with a field f of type string. Right? As easy as that. We can also add runtime annotations. Again, we can choose to have the type loaded, but, and that's important, we can interoperate with class files without loading anything. This is important because you can guess if you have, for example, a static initializer in your class, and you would do reflection, for example, in the build tool, you would load the class and you would execute the static initializer in a phase where you're not intended to run code. And of course, you normally don't do anything tragic in static initializers, but especially if you download something from Maven Central and you would process code in your build environment, this static initializer could access your file system, it could access your SSH keys and so forth. And there's examples of how this was done in the past, that people try to sneak malicious code into your machine by putting it on Maven Central, stealing a popular library from before, publishing a small update, and adding something to it. So by using the class file API, you can just parse the byte arrays without any possible code execution, and that's why it's, especially in build phases, much more preferred to use these approaches rather than loading and executing. Right. So it's pretty straightforward from there. As you might expect, the class file API isn't supposed to be complicated. It's supposed to be a proper representation of the format. This way we can also add a method. Now we have to add a method type description, not a single type description, which we concatenate by adding the return type and the parameter type. And further we add a modifier. This time we have to tell it what modifier is before, and then we build the method. So I mentioned the code attribute, and in order to talk about class files, we also have to talk about bytecode. Those two things are often used synonymally. So people talk about bytecode when they mean class files and the other way around, because class files aren't complex. Bytecode, on the other hand, unfortunately is rather complex. Again, Java trivia, bytecode comes from the era of applets and is organized as a stack language. It is, however, implemented in a code attribute in the Java class file, and we'll rather walk through it. A small example of Java bytecode: how would Java-C translate this method to a code attribute, right? In order to translate or compile a method in Java, you have to understand the abstraction that the Java virtual machine defines for that. And the Java virtual machine defines code as a stack machine. And now if you think back to your university days, you might remember what a stack machine is. The reason why you just might remember it is that even if you work with hardware, there's no such thing in hardware anymore as stack machines. Modern processors use registers, you load data into registers, and you execute operations on these registers, like 1 + 1 is load number into register 1, load number into register 2, execute instruction 1 + 1, and load the result into register 3, right? However, in the world of applets, there were two important things. The first important thing is that the bytecode language was supposed to be as narrow as possible. In order to do so, you wouldn't want to have register addresses in your bytecode. You would just have a stack language where every instruction implicitly is executed on the top of the stack. Means, on average, it's half size. So when you loaded your applet on your Netscape browser through your modem, this was very important back in the days. Today, it's not important anymore, but without these decisions, Java probably wouldn't have been as popular in the days back. It probably wouldn't have made back its money. It probably wouldn't exist anymore. So this is just the price anything that survives as long as Java will have to pay. So first of all, we have an argument, which is called the local variable array. And then basically, for example, you will have supplied the number 25 to the function add. And then we have this operand stack, which is the stack language. And then we have instructions, so how operand languages work. First, we load the value onto the stack, first thing. Then we load 42 onto the stack, 42. Then we execute plus, pop the two top values and push back the result. And then we pop the last value of the stack and return it to the person who called the method. This is, of course, not what your computer will be doing when it executes a Java program. As you all know, the JVM has a JIT compiler, which basically just looks into this representation of the method, which is stack-based, and then it compiles it to a proper executable. It optimizes things. It might not even do any of that anymore when you inline a lot of methods and come up with something much faster. If it did that, the JVM would be very, very slow, and Java used to be very slow, because in the old days of Java, before there was a JIT, the JVM would basically execute instruction after instruction and emulate the stack language, right? Also, the reason why Google didn't use that for Android, JIT compilers work very well when you run a program, you boot it up, right, and you let it run for quite a while, and then it has time to optimize it, and when it actually is up and running for a while, it will be super fast because it's optimized, right? Android, you open your phone, you open your app, you're already bored on whatever's happening on Facebook, so you close that again, and all the compilation is back to zero, right? So that's why they compile it to a different bytecode representation where this is not the case. Anyways, all these things that we just mentioned are a so-called bytecode. And in the class file API, you will be able to trigger these bytecodes and then basically add it to this attribute that is the code of the method. So just as before, we have here the code builder. We say code builder iLoad 0 from the 0 offset, right? This is the argument to the method here, 0. Then we load the number 42. Then we add the numbers, and then we return the numbers. I mentioned at the beginning, you will likely never do this in your career. You will likely never work with bytecode directly, and that's the reason why ByteBuddy, for example, has become so popular. This is nothing you can add to a project for your customers, for example, and expect the next best person to come in and change something. They will not be able to understand that. They will not necessarily know bytecode because you will have to read the specification. There's my YouTube videos on it. Other than that, there's not much material on explaining bytecode. And there's many, many more instructions than that, of course, and this is just the surface of bytecode manipulation, so it's always better to not generate bytecode directly, but I'm sure that the power users, I'm expecting, for example, the Spring framework, to generate their proxies using that directly to avoid a dependency that they currently need. Right. So also, just to demonstrate why working on bytecode typically is not a good idea, all I did now is I removed the static, right? What does that mean? That means that the first argument to the method is no longer the value, it's the disreference, meaning that what we do here, every reference to a variable in your code will have to shift by 1. So a manipulation of a method as trivial as making a method non-static is a pretty invasive change on the bytecode level, and nothing you would normally want to do. And again, this is just an example why bytecode manipulation normally is not a good idea, right? So also, if you want to do additional local variables, this will now change the beginning variable array. So in theory, you have to think about all the variables you want to assign already before you create a method, and then adjust it accordingly. This is again something that ByteBuddy, for example, would do for you transparently and allow you to change rather easily compared to this direct manipulation. In the class file API, what you would need to do is you would say code builder, allocate a local variable of type integer, then you get a resulting offset, and then you can store something and load something without going into too many details. All right, I have 15 minutes left, so I have to prioritize a bit. Yeah. Another thing that you have to be clear about when you work with bytecode and you want to do your own bytecode manipulation is that Java is a very high-level language. Java bytecode is not. If statements, while statements, for loops in Java are structured branching on the Java bytecode level, and many of you might have known that from before. Everything you get is the goto statement because it's not very man-friendly. Goto is, of course, something we avoid today. No programming language has it anymore. That is fairly modern, at least. Instead, it is, however, very machine-friendly. Machines like to go to statements because it's clear. There's no complexity to it. You just evaluate a condition, and if the condition is true, you will jump to a certain offset in your code. And you can imagine if you have this list of bytecode instructions, you evaluate something, you jump to a different offset there. That's something you can execute quite performantly, and this is something also that compilers like. If you look at the JIT, it has a sea of nodes, basically identifying every segment of jumpable code, and then it merges them in a way that it thinks is optimal for execution. Right? So this is every Java program will basically compile an if statement to an if block, and then it executes the if block, and then it will have a go to the end of the else block if you execute the if block. And this is basically how it's set together, right? In the bytecode API, yeah, just jump. In the bytecode API of the class file API, I would say this is, however, solved pretty conveniently. It allows you to take the high-level constructs of Java and trigger them in form of concatenating lambda expressions. So instead of having to create your own if-else, it will have a template where it does that for you in the background, and you only have to tell the class file API where you want to jump, or what you want to do in case of if, and what you want to do in case of else. Right? So you'll be able to do it like this. However, However, you can, of course, do it manually, and this is how bytecode manipulation has worked so far in most of the Java libraries that did bytecode manipulation. You would have to create labels, and then you would have to say, this is if check, and in the end, you say, this is where I want to jump in case of else. Then I have the go to, the unconditional, in the end block, and bind the end block as well, and manipulate that. You can imagine also that if you want to manipulate bytecode, you will have to look at this kind of bytecode representation, and if you now hibernate, right, and you want to add this dirty flag somewhere and add this if statement, you will have to process what your code is meaning to represent in the worst case and bring it back to something. It's also what decompilers have to do, right? A decompiler, that's why Java decompilation is pretty difficult. If you want to have a class file and you want to translate it back to Java, the decompiler will effectively need to walk through this list of statements, find out what the if block is and what the else block is, and then obfuscate this again, will try to shuffle this around in a way that the decompilers will struggle to understand what an if statement is. And that's kind of the ongoing war, you could say, between decompilers and obfuscators to basically, because also the obfuscator will have to retain the original logic of the bytecode, but it will still try to make it hard to map back to something, right? Okay, I'll jump over stack map frames, which is a more complex topic and takes some time, and rather go into reading class files. So far we've just looked into a very basic view of how you can create class files. Again, this is something that a lot of libraries do, as I mentioned, Hibernate, Mockito. But if you want to manipulate an existing class files, you will have to read the class file first and then transfer it. Of course, the class file API can do this as well by taking a class file, an empty one, and then you parse a file, a stream of bytes, and will get a so-called class model. The class model, for example, you can now say, I want this class, I want the name of the class, and you will get a UTF-8 entry, and then you can transform it to a string and saying what the class's name is. You might think, why not use reflection? Why not use foo.class? But I already mentioned it. If you use foo.class get name, you will load the class. If foo.class will have a superclass that's not available, let's say a dependency that is optional, right? If it will have a static initializer that runs code, then this code will run. If there's a field that references a type that doesn't exist, the loading of the class will fail. You will get a verification error, right? With this API, you can do this safely. So if you, in some context, process untrusted code in your Java applications, you should consider using this API. This is actually one of the use cases I see for myself can be more broad than the people working at the back end of libraries, right? And yeah, that's one of the uses I see for myself. I expect also build tools and so forth to use more of this, like let's say the Maven Shade plugin, right, that renames a class, or other build tools like find bugs that wants to go through the class file and see if there's a pattern that it marks as suspicious, right? They will be able to hook into these APIs and read classes that way. With the class model, however, you can also do the manipulations that I mentioned. And since this is only introduced in Java 24, it is very much focused on modern language features. So it does this switch case statement on code elements. So for example, here we have a method, then we say, for every method, give me the method model. Then we check the name for the method model, and then we say, okay, for the method model, give me the code. If the method has code, meaning it's not abstract or native, give me every code element. And now we're back at the bytecode instructions, right? So we get, for example, an invoke instruction, which is a method invocation. You have a method that invokes another method. Give me the owner of this method. So if foo calls a method on instance class bar, then owner will be bar. If it accesses a field of bar, owner will be bar again. Right, so you can, and all the others, you throw a runtime exception. Of course, this is because you're not done here. There's a long, long list of bytecodes, and it's way too many of them that we can go through it, even in a dedicated talk. But this way, you can, for example, take a class. This is something you cannot do with reflection. You can take foo, and you can check what fields and what methods does it access. And if you have some, for example, you have a tool that wants to avoid that this package calls methods from this other package, right? If you wanted to write code to check that, you could go through the class file doing so, and just go through the instructions that are method and field accesses and validate that this is not happening, right? Yep. So now that we have written classes first, and now we've read classes, we can of course look into transform classes, and there again, you can say classfile.transform class in the class file API. And the easiest one is where you just say with, meaning that you just retain the class file as it is. Every element you will get from the class, you will pass on to the class you're writing. Once you've done this, you can of course extend. You can say, all right, I want to transform methods. Again, every method model you encounter, you will now transform. Simplest implementation, just passes it along. And then we can say, all right, for every code model that we find in these methods, again, we want to copy them as they are. But now you can start saying, all right, if we encounter a class named bar in foo, we can just change the name of it. And that's, again, how, for example, you would implement the shade plugin in Maven, right? You would walk through the code elements and through all named elements of a class file, check them, just pass them on to the transformed class unless they have a name that you want to change, right? Or if you want to replace a field access with a getter call. Then you can just transform the class and see if a field is accessed, and if you encounter a field has a getter, you will replace the field instruction with a method instruction, and yeah, that way you, in a way, can implement your own Lombok plugin if you wanted to. And that, again, that's how Lombok under the cover also works. It just not with the class file API, because it's so new, nobody really uses it. Let me check the clock. It is 47, so I'm running out of time even more. Then I'll jump through line numbers and rather go through how it, my slides, by the way, are often optimized for having other talks. Let me rather look into what this means. So the problem so far, and this is what I mentioned in the beginning, is that whenever you update your JDK, you will likely encounter that your libraries won't work. As mentioned, Mockito, if I implement Mockito today, I can support Java 25, and we actually do support Java 25 because Java 25 is already available as an early access release, right? I can download Java 25, I can run Java 25, and I can read the specification of Java 25. So I know what the class file format means, right? However, I don't know anything yet about Java 26. So if I write Mockito today and ship it to you, and you download it and you use it, and now you want to update to Java 26, I cannot transform a Java 26 class file. And if you want an intuitive version of that, let's say I wrote a Mockito version that works on Java 7, and now I ship this to you, and you run it on Java 8. Suddenly, you see a lambda expression. What's that? I don't know, because at the time I've written Mockito for Java 7, I didn't know what a lambda expression is. The same goes with, for example, permitted subclasses. In the old days, Mockito was creating subclasses for mocks as instead of inlining them. But if I suddenly received a sealed interface, right, for Mockito, I would try to create a subclass implementing the interface, and then the JVM just will say, no, that's not how this works, right? You're not allowed to do that. But that's impossible to anticipate. However, that's fairly rare, and that was the annoying situation we've had, right? You would have to update Mockito every time we shipped a new JDK was shipped, with all the feature changes we had, with all the breaking changes we potentially had, even though the JDK itself has not changed the class file format. Class file formats between Java 7 and Java 17 were still sort of common. We've had permitted subclasses and sealed interfaces. We've had records. We've had, what else do we have? We had constant dynamic, a new bytecode constant. We've had invoke dynamic. But since Java 17, I would say the missing bits have been inserted to the degree that the changes are pretty minimal, right? And I'm waiting for value types, which I'm sure will have some implications. But in between, if value types is shipped in Java 27, you shouldn't need to update Mockito for updating Java to Java 26, right? So, but if I wrote it now in 24, the class file API for 25 will know how to process the class file for Java 25, because this is now not shipped with Mockito, it's shipped with the JDK. And by just plugging Mockito into the class file API, I leave the hard work of parsing the file and making sure it's parsed correctly by the specification to OpenJDK. When you now update to Java 26, this knowledge of how to parse Java 26 class file is shipped together with OpenJDK, and Mockito will just be able to run through the instructions that are the same instructions as Java 25. What's different is, however, that the JVM itself can assure that this is the correct way to parse a Java 26 class file. If I implement this myself, the bytecode processing, I cannot be sure. I will see Java 25, I've never seen this, I don't know what to do. I will have to fail because bytecode errors are hard errors, will crash the JVM worst case, right? Only if Java 27 now introduce value types, something new. Only then there's an actual change in the class file format. And then you will have to update Mockito to allow addressing that. The way OpenJDK wants that to happen is that you add basically a meta-inf, a multi-release class version of the class file processor to your jar, and then it will support Java 24 and Java 27, because that's the disadvantage. If I compiled everything with Java 27 now, you would have to update anyways. Like, you couldn't run this new Mockito versions on OpenJDK 24 anymore. So instead of the library forcing you, the OpenJDK forcing you to update the library, now the library would force you to update OpenJDK. Wouldn't be a great version either. So the recommended convention for bytecode processes like bytebody is doing that, right? To mention that, of course, we've done bytecode manipulation before Java 24, obviously. You've used Mockito before Java 24, and the most common way of doing this was ASM. I think most of you might have heard of ASM. ASM is also being used by OpenJDK itself to generate class files. Like, for example, for lambda expressions. Lambda expressions are nothing more than ASM-generated classes that call one method, right? That is the lambda code. So with ASM, you would basically have a class reader and a class writer, and then you would pass visitors in the between where you could manipulate things. Pretty simple, and this is how we've done it. bytebody uses ASM under the covers. It's a very good library to manipulate, but it's not state-of-the-art in the sense of how the API works. It's much more rough than the class file API, much harder to use. To me, this doesn't make much of a difference, because the people who work with bytecode manipulation normally have read up so much that they can use either library. But this is how all code is written, and it's completely unrealistic to me to rewrite bytebody using the class file API. So how would I offer the service? And spoiler, I'm already integrating the class file API. It's as easy as basically saying, before I go there. So with ASM, the nice thing is I write something with ASM in Java 24, right? ASM knows how to process the class file. But the moment you update to 25, you have to update ASM. Most of the times, ASM will just say, all right, I know Java 25 looks exactly like Java 24, so that's fine. But you will still have to do this update. This is what I mentioned, right? This is why you always have to update your libraries. But then Java 26 comes along, you again have to update ASM, and then Java 27 comes along, then you doesn't fit to update ASM anymore. Now all tools that use ASM actually have to integrate the new features that ASM offers to process these new class file properties, right? So now you have to rewrite everything to Java 27 and fix it. The nice thing, however, is other than the class file API, you don't need to have a multi-release jar file, because now the class file processor is not shipped together with the JDK. So basically, ASM itself knows how to do Java 27, but it can still run on Java 25 and Java 5. And both bytebody and ASM still support Java 5, simply because a lot of legacy companies that need tooling, like, let's say, OpenTelemetry, right? How does the agent inject itself? It uses bytebody, and then it should run on old apps. Otherwise, your OpenTelemetry graph would be broken, where this one important legacy app that hasn't been updated is running. So what I did, I basically implemented a bridge from the class file API to ASM and back. So I could leave all my code in peace. I had to not change a single line of code, but add new processors that basically delegate back and forth and then basically call it. So all you have to do, if you have ASM code today and you want to upgrade to the class file API, is that you substitute your class reader with a JDK class reader, and substitute your class writer with your JDK class writer, and this is all built up top of ASM, right? And then the API is identical, it's the same types even, so you can substitute it. So now you let OpenJDK parse the class file, delegate the information on the class file to ASM, have all the processing done in ASM, and then parse it back. Nice thing is also you don't have to run multi-release jars, and also again, like for complex classes of many thousand lines of code, multi-release jar is just not a good option, because you have to copy-paste the entire class and just have it duplicated, right, for each Java version. And that way, yeah, it's not only me. I think basically everybody who does bytecode processing is already jumping on the train, because it's a very easy update. And I think maybe in the future people will navigate more to using the class file API directly. But for now, I think we can expect with Java 25, most tools will adapt to this approach. And by saying that, the bytecode community is fairly, fairly small, so we talk to each other, and that's my impression at least. And also in ByteBuddy, if you use that, you can say, I want to use the class file API first, but by default, you just use asn, and only if you encounter a JDK version that the current version of ByteBuddy doesn't know about, you will have to, or ByteBuddy will implicitly use OpenJDK's parser, right? And we've integrated that, and with Java 25 will be the last update that will force you, likely, to update most of your libraries. At least that's true now for everybody who uses ByteBuddy, which is most bytecode manipulation libraries in the Java space. So my hope now is that once you update to Java 25 and you pull all your dependencies to the latest version, from then on, you can just run your apps on all JDKs that are coming, unless they include major changes to the class file API. So yeah, that's the hope and the intention, and I know there's a lot of details in here that you will instantly forget once you walk out of the door, but hopefully you understand why this change is very hidden but quite significant for the Java space, and that's also the only reason why Oracle introduced a so complex and so big library into the core OpenJDK API, into the Java base module, to allow libraries like mine and users of libraries like mine to avoid this constant need to update the JVM. So I think this will be very beneficial to especially enterprises, but hopefully to you. And I have 40 seconds left, so I'll just give up here and say thank you for coming, and jump over this and rather end it here. As I said, I'm Rafael. If you're interested in these things, you find me no longer on Twitter, but you find me in Blue Sky now and on my webpage. And yeah, check out ByteBuddy, documents for Jay, another thing I do. Thank you so much for coming. Have a good rest of the conference. Yeah, and if you have questions, I'll be here and around for the rest of the day. Thanks. Cheers.